Thanks very much for the introduction. Thanks, organizer, for the kind invitation. It's very nice to be here. So, last time I was in Europe is about almost 5 years ago. So, very nice to be back. Okay, so this continuation of Robin's yesterday talk about ghost conjecture. Let me first state the original conjecture from Ruochuan and Pollack. Sorry, Bergdall. Big slope. Rectangular representation is irreducible and will restrict to PQP. And we assume it is reducible. Also, we have rho bar is a restriction on inertia subgroup, which is of this form. Okay, I think Jobin's talk yesterday. Okay, so the question is, we are interested in the periodic slopes of the R bar part of the overconvergent periodic model forms. So that is the slopes of the characteristic power series of this UP operator. Okay, the double star is just ovate. Equal to slopes. We can compute the slopes in terms of somehow a combinatoric way, in terms of the it's called Gaussian series, which is only depends on rho bar. Okay, so one of the main ideas of this work is to realize that this is a purely local story. So yesterday we formulate a local analog of this ghost conjecture. So, okay, so we define the so-called OKP projective argumentative modules. Of type rho bar. Okay, you already used H2 to denote such a module. Okay, that we can define various abstract forms. That's more forms. Forms. Okay, then we can define. Similarly, we define the characteristic power series of UP. And also those series. Okay, then the main result of yesterday's talk is that in the primitive case, that is the multiplicity of H tilde is 1. Okay, so if H tilde primitive, the multiplicity is 1. Then these two power series has the same Newton polygon. The first one, C tilde, is equal to the MA of the those series. Okay, the goal of this talk, the goal of today's talk is to use this local story for the original conjecture. Okay, so in fact, we can apply this local analog to this are localized part, complete homology. Okay, if this R bar localized part is primitive, then we can just use this the theorem to conclude, and we are done. But unfortunately, so this primitive, this condition, I think requires some multiplicity one condition in general. Perhaps it is not true. So okay, so the main point of my talk is how do we treat a general case from this primitive case? Okay, so the main idea is that for this Gauss conjecture, it's only about slopes. That means it only involves a spectral variety. But the idea is that we upgrade story to eigenword. Okay, so we can use more structures to compare the slopes with some local data. We will see this later. So we first upgrade this concept of this OKP, projective augmented modular. Let's give the definition. Okay. We call it projective arithmetic modular. Just an OKP, projective augmented module. Module. And together with rho bar, type rho bar plus continuous left action of rim deformation rate. Okay, action. So unfortunately, both these two notations is OPAM. I cannot simplify the notation. And such that the left action commutes with the right GL2B action. So left. It commutes with right GL2B action. So in the augmented case, it chooses certain projective envelope over the ring of AP, not over the sigma AP. There's a multi representation for this survey with certain multiplicity. Okay. And the third condition is that the classical forms. Okay, so for a relevant character E and with K satisfies some congruent condition. This is only for, I think this is only for, sorry, this is only to infer that the unramified, okay, the space of unramified flows exists. In this case, this Galois action, the action of the rim deformation ring factors through the crystalline deformation rate. X on this unramify. Okay. Factors through the crystalline 1 minus K. Epsilon 1. Okay. And of course, we require the compatibility of a high action and this the action of this deformation rate. Impact Galois relative. We impose this condition is just for construction of eigenvalue to employ the eigenvalue machine.
So is that a integral statement or just after the repeat the compatibility of Hecker and Galois?
Integral statement, I think.
It means you're using a symplectic Hecker algebra and comparing with the.
Yeah, I think like UP, I mean, right? Yeah, the example is again, you have this R bar localized with homology. Another interesting example is from the patched complete homology. But the patch module is too big, so we need to specialize. So that at infinity, I think this is instructed in the 6 authors paper. Yeah, so you have the action of Galois. And also you have the action of S infinity, right? Auxiliary variables. Yeah. Yeah. Okay, then if we specialize, you get our arithmetic module. Specialize. Why? Why is just of the S infinity. Yeah. So this type's module is important for our later argument. But unfortunately, because we don't know like multiplicity fund for this M infinity, so we use something similar but different. It's the Pascunas module instead. MY is naturally, yeah, as I said, MY just naturally an OKP arithmetic projective arithmetic module. Okay, let me first state the theorem. For every weight, we know. Okay, and for H, it's just our any OKP projective arithmetic module. Newton polygon of this tube. That be just it's the same as the Newton polygon of Gauss series, but after some stretching, that's the point. The same as Gauss series. But we stretch. Stretch. Sorry, how to spell this? All right, stretch both X and Y direction. And it's of course, I mean, it's very natural to expect that it's stretched by the multiplicity of this H2. And actually, this theorem A, we just concluded the Gauss conjecture. Right? That's A. That's the Gauss. because it doesn't require primitive anymore. And to prove theorem A, we need another theorem. So we can compare the ghost slope with certain local data. Just the slopes in the appears in the triangular deformation space. It show up in yesterday's talk in Helm's talk. Part 2. P to be the rigid analytic space. One try, I think. The characters, continuous characters of cross square. There are the truncated deformation space. Space. I use the notation X frame trend. Also, inside this space times T. Okay, this first introduced, I think, by Helmut, later elaborated by Helmut and Roy. Okay. The theorem B is that the ghost slope is exactly the same as the slope in the triangular deformation space. Okay, suppose you have this X 1 delta 2 triangular deformation space. We have corresponding weight. Star. Yeah, I think our normalization is like 1 delta 2 inverse pi inverse. This is periodic subatomic character. P. This is like generator of the ZP cross. Sorry, it's like 1 plus ZP. Okay. Okay, then the point is that if 1P has positive periodic valuation, I call this as a triangulating slope. Okay, the slope for this triangulating points for this point in the triangular deformation space. I call this a triangulating slope. Then number is a ghost slope. Ghost slope. Okay, let's go stop. Conversely, every ghost slope appears as a triangular slope. Ghost slope. Appears as triangular slope. Okay, for some X delta 1 delta 2, and the relation is like this.
Ghost slope means it appears for some projective arithmetic module, or
every ghost slope of this one. Yeah, for this weight.
yeah, for what? For which ghost series? The ghost series for a particular H tilde? Or?
Yeah, the ghost slope is only depends on the row bar actually. You have this ghost slope for this weight, and this only depends on row bar.
It doesn't depend on a choice of H.
Sorry?
Doesn't depend on a choice of H tilde.
Yeah, that's the point. So that's a good point. So in yesterday's talk, you have such H tilde. So you can define the ghost series, right? But actually, the ghost theory only depends on row bar. You can prove that.
So even when you increase the level outside P.
You want to do what?
when we include the level outside P in the cohomology, for example?
Yes, yeah, we fix the bar. Yeah, this closed series it only depends on the bar. Yes, all right. Yeah, even
I mean, the multiplicities change, but the
yeah,
slopes
but
stay.
but slopes are the same.
Ah, okay.
Yeah, that's the point. Yeah, our definition depends on adjuvator. But you can prove that after find the power basis, certain basis you can prove. That's actually. Okay, any more question? Okay, so rest of the time I sketch these two theorems. The first step is how do we use theorem B to calculate theorem A, our main theorem. Okay. Step one. We have a arithmetic module. Okay, we are concerned with the UP slopes of this sky. Slopes. First, we can conclude that using theorem B that it's actually is contained in those slopes. This we just for this point we just use eigenword. We use eigenword machine, for example, there. You have eigenword beta maps of spectral variety. As and over that this is the conformation space. This space, and this is just a space. Like this, right? And you have this 2W with space. This is beta map. Okay. Yeah, and this is certain. And this space is actually a subspace of this deformation space times T. And there are certain way to write image of that. Sorry, this is a point of like this, x star. Okay. You have such a point. Okay, then you have associated a point here. And it claims that the image of this eigenvector, if you match down to this product, image lies in the triangular deformation space. Right here. This is triangular deformation space. This is just using the density of classical points. Okay, so now okay, actually you can x1 beta 2. Yeah, this is a certain formula to write down beta 1 beta 2 from this data. So I just write one thing which is relevant to us is that the 2p. It's AP inverse. Okay. So now theorem B tells us that We have a point in the spectral curve. Then this the slope. This is slope of pt is just equal to factor slope of delta 1p. Right. So prove that this is a dose slope. This is the first step. Okay, the next step is to show that the multiplicity is just by stretching the multiplicity of H2. This way just there we go. Okay. So here we just use an argument, the Q's argument for finiteness of homology. Okay, for fixed n, we consider Vn. It is the subset of the weighted space. It's points like n. Also the Gn at the start. Okay. It's just a point in the ghost. Okay. It's just a point for this ghost theory is to define the Newton polygon. Okay. This point is its vertex. At the point. And when you get to the plot, you know that this is actually just a complement of finite enclosed disk. Money. Say B one, the one B M. Okay. Okay. Then we consider some this is like the Stein space. So we consider this in delta to number. So this is like this is like 1 minus epsilon. That's 1 minus delta. Okay, boundary is open. So now we have a closed boundary. The radius is less than or equal to 1 minus delta. Remove the open disk with bigger radius. Okay. So now this is affinoid. Okay, this is affinoid. For this affinoid, we can apply the Maxwell value principle. Okay. So now we will use the result step 1. That is, we know that slopes are all ghost slopes, and once this vertex of the ghost Newton polygon, we know that the difference between two slopes has some positive value. Positive value. Okay, so then the claim that for such delta, there is an even smaller maybe number epsilon delta, such that the following two spaces coincide. Following coincides. consider the part of the special curve that we call this n and delta in the space. Of course, the weight is that v and delta, and we consider the jump of the slope. So, sorry, not AP. It's yeah, it's AP. Yes, sorry, this AP. It's less than left slope at end of the Gauss-Newton polygon. Because this xn, it is a vertex, as I said. Okay, the left slope and right slope, they have a positive difference. And because this is affinoid, you have applied this maximal value principle. So that this means you have to find the lower bound of the difference. So that is, we consider the space plus. So this is plus. Okay. This two space should be same. Okay. We can find a sufficiently small epsilon delta such that as long as the slope is less than left slope plus epsilon delta, you should have this smaller than the left slope. Okay. Here's finiteness argument. Turns out that this part of special curve is like finite over weight space. And because of the Bose machine, we also know that this is flat. So losses. Okay. Well, we have that. This is finite flight and of constant degree. This it's finite flight over the weight is. And also because this is irreducible, and so this like finite of constant degree. Constant degree. Yeah. Okay, then the next step is just to simply compute the degree. Then we can pick any points, satisfy this condition to compute. That's a relatively easy job. We just choose the special, some kind of special points. So as explained in yesterday's talk, you have this D Arami-Phi and D Iwasawa. Okay, these 2 points should have a line in the polygon corresponding to the new forms. So choose this A. Okay, this should be this Vn, and for n equal to times this is sort of be 1 times. Okay, for those points, this is you can check that this is in Vn, and this implies that the way of the this part n over this Vn is just equal to the dimension of this. Yeah, the rank of this space. Okay, let's see. So this is equal to. That's equal to. Yeah. So this number goes through every O. So this is goes through O. So every n, so you can use some kind of points to prove this degree. Okay, so now we can conclude, right? So suppose this is goes Newton polygon. So DO polygon like this. Okay. For certain weight. Okay, so at each vertex, you know that the slope equal or less than equal or less than this slope, the left part of slopes. And total multiplicity, like for example, this is n. That's the n times the multiplicity of H2 for next vertex. L. Okay. And the total multiplicity is L times the multiplicity. So you know that. Okay, in between it's just a slope of this line segment, right? Because we know the slope O contained goes slope. So the slope between these two sides, exactly just one possibility. And the multiplicity is just it's just one m times, sorry, the multiplicity of H2 times this L minus n. The theorem A. Okay, so I'll sketch the formal theorem B. So far, we haven't used much of the result of yesterday's talk, right? Like the local, the theorem for the local ghost. Okay, so for theorem B, we really need this result. This.
Did you use part 2 of theorem B? Every ghost slope appears as a. Did you use? I'm just wondering if you used both parts of theorem.
I think, you are right. Yes, I only use part 2 of the theorem B. Yes, all right. Yeah, thank you. Yeah, I only use that part.
You use part 1 in the first. Use part 1 to prove that slope of UP were slope of.
Yes, yes, of course, part 1 is sort of meaningful, of course, but I think to prove the theorem A, I only use the second part of the theorem B. I only need that. I only need that. The UP slopes is contained in those slopes.
That was part 1.
Part 1. Oh, sorry. Okay.
Okay,
I
that's
use
the,
part 1.
that's the only part.
Yeah. Sorry about that. Yeah, I only use one part of the theorem B. Yeah. Okay. So here's theorem B. Okay, so the idea is to really apply the local ghost conjecture. So to apply local ghost conjecture, we need some printing module. So as I said earlier, this patch module is somehow a good candidate for that, but we cannot verify the multiplicity one prediction. So instead we use Pascunas module. So we have this Pascunas. The fix, I think the local character. So we have its category because C theta. And you have this P local long length of this RT bar, which is principle here. And Mascunas module, if I write correctly, is just projective envelope of I1 R. Take a dual envelope. So I1 bar dual. Category C. Okay, so see that already something project envelope. Okay, this is of course somehow primitive. So we use starting from this module to construct some. So we know that it's okay. All right, I forgot to write this. Then we know that this is big work of Pascunas that anamorphism ring of this Pascunas module is just a local deformation ring. And in our case, we use frame deformation. So frame deformation is like, I think you need to add like 5 variables. U, V, V1, V2, V3. So these 3 variables, V1, V2, V3 is for the frame, and this is 2 guys is for the determinant. Okay. Okay, then the key step, which is actually not very difficult. So we construct some family of this arithmetic module. To the frame, which will receive the action of this frame deformation range, as well as the other 2 pieces. And such that this module is actually isomorphic to projective envelope. Frame. What is F as frame? It's similar to this as infinity. We have some auxiliary variables like this kind of thing. So this frame is here we have this U X. Okay, this is just some technical thing. But here X is in field, but not in the square of that. I is uniformizer. Time is the maximum idea of the deformation rate. Not frame one, it's just deformation. Yeah, there's certainly some technical condition. We just need to, because we need to this to be projective things. Okay. We have such stuff, then we can use eigenvalue machine to conclude. So note that for any y, like y of this as frame, okay, prime, and have a similar thing. Frame y, like a specialized at y. This is arithmetic module. So this and primitive is primitive. Oh. Projected. Okay, for every y. exactly similar to this patchwork patch module case. Okay, so now we use eigenvector machine to compute. Now we have, and we use eigenvector machine to this tutor frame, and this is inside this frame deformation and amplitude. This is 2 copies of dump this time, because we also vary the determinant times GM break. Okay, another thing like that. Spectral things. Inside this attitude. Okay. Okay, so now we want to compare this eigenvector with the triangulating deformation space. Okay. Consider map U e to this 2 times GM rate. Number 1 compare delta 2 from CP plus, and this is delta 1 chi inverse plus, also delta 2p. Okay, and the claims that right here, sorry, Utah reduces okay, isomorphism between reduce the structure of the eigenvector with the triangulating deformation space. This is reasonable, although you just had 1 GM, right? Had 2 GM here, but because you have the delta 1p times delta 2p is actually determined by x. Okay, so delta 1p is exactly determined. It is also, so delta 1p is determined by delta 2p and also x. Okay, so this is reasonable. So this is reasonable. I think this is somehow well known to experts. Maybe this work by Hamilton on this locally analytic Jackie functor, and maybe BHS. It's not BHS. But finally, we cite the work of Bergdall and Dean. Yeah. With that paper in Peking Mass Journal, I think. Okay, now from this we can final conclusion that, so we know that for each y, slopes of P2 to frame y. Okay, this is equal to the ghost slope. Of this ghost slopes, just ghost slope, actually of rho bar. Only depend on rho bar. That's the key point. Every y. If you put it together. Okay, then you get the slopes on these eigenvertices, but this coincides with the Franklin slopes. And for each y, they are the same. So every piece is also equal to the triangular slopes. One. Okay, so and this way we prove theorem B. Okay, maybe I run too fast, but finally let me say that the theorem about reducible components of spectral curve. One. Fine. Okay, under the same assumption. The spectral curve has at most on this scheme, reducible components. So you see that this this is actually an effective bond of this reducible components of the spectral curve. I think it is also the same as the reducible components of eigencurve. Yeah, I think this would be a very interesting problem to really work out this multiplicity in examples. Yeah. I'm sorry, I finished too early, so I'll stop here.